Hey guys, in this video we're going to be talking about a rule that is going to be helpful in solving some limits that maybe we weren't able to solve back when we were doing our limit in Unit 1. So we're going to be using derivatives in this section to do limits. And the rule that we're going to be using is called L'Hopital's rule. This word is always fun to have people try to say what they think it is. It's a French word named after a French mathematician. But yeah, it's pronounced something like L'Hopital. That's how I pronounced it. And it was named after this guy. And there's his full French name, Guillaume Francois Antoine Marquis de L'Hopital, something like that. So he was a French mathematician. He added some important things to calculus, like something called infinitesimal calculus, and was very intelligent, as you can imagine. All right, so the rule that he came up with is this. If we're given two functions, we'll call f and g, and those two functions are differentiable, meaning we're allowed to take their derivative. And the limit as x goes to c of f of x over g of x. So in other words, this is for rational functions. Rational just means a fraction function, essentially. So if we got one function on top of another function, and we try to take the limit, and we get what's called an indeterminate form. So these are indeterminate. If we get an indeterminate form, meaning 0 over 0, that's indeterminate. It is not 0. You can't have a 0 over 0. Or if we get like plus or minus infinity over plus or minus infinity, those are all called indeterminate forms, meaning there's no answer. We got to do something to this function to make it work. So if that is the case, well, he found out a little trick that we can do. And that is we can take this original limit as x goes to c of f of x over g of x, and we can simply just take the derivative of the top and take the derivative of the bottom, and then see if we can find the limit. So all we do is just take each derivative, do them separately. Do not do the quotient rule. So two disclaimers here. One is do not do the quotient rule because we're taking each one separately. So you don't want to do like f prime times g minus fg prime over g squared. Do not do that because, again, we're doing each one separately. So do not do the quotient rule. And the second thing is we can use this as many times as necessary. Use as many times as necessary, meaning we can take the derivative once. If we still get an indeterminate form, we just, try to take their derivatives again. We still get an indeterminate form, we do it again. And we can keep doing this. Sometimes will pan out well. Other times, maybe not so much.
Your bus has arrived.
Sorry.
All North students, you are dismissed. Have a wonderful holiday.
All right. So as I was saying, you can do this as many times as you want to. If it goes more than 2 or 3 times, generally that means you're kind of off on a tangent. You're not going to end up finding it. But sometimes we need to do it 2 or 3 times. So let's go ahead and look at some problems here. All right. So this first question, anytime you try to evaluate a limit, if you can think back, the first thing that you want to try to do is just plug in what's given and see what you get. When we do this, we would get 2 cubed minus 7 times 2 squared plus 10 times 2 over 2 squared plus 2 minus 6. And as you can probably guess, in this case, we should get 0 on top. Yeah, 28 minus 28, and a 0 on the bottom. This is called an indeterminate form. Now, what we have done in this, when we got to this point, what you were supposed to have done before is factor the top. So the top, you'd actually need to factor out x first, and then this would factor into x minus 2 and x minus 5 for the top. In the bottom would factor into x minus 2 and x plus 3, right? And then you could cancel there, and then you could try to find the derivative. And it turns out it would actually work in this case now. So then you would try to do the limit as x goes to 2. You would plug it in. You would get 2 times negative 3 over 5, so negative 6/5. All right, so it's possible using what we know. However, some of these problems are going to be the case where we can't factor them. And this way actually is a little bit quicker in some ways. I'm using L'Hopital's rule. So this was doing it without L'Hopital's rule. However, if we do want to use L'Hopital's rule, so we do get an indeterminate form, generally I just make like some sort of notation. I just sort of do like L with a little apostrophe H. There's not really any standard way you're supposed to do it. But I'm just showing that we're going to do L'Hopital's rule. And then I'm just going to rewrite it. Limit as x goes to 2. I'm going to take the derivative of the top. So that's 3x squared minus 14x plus 10 over 2x plus 1. Because the negative 6 goes away. And then we just try to plug it in again. So then it's 3 times 2 squared minus 14 times 2 plus 10 over 2 times 2 plus 1. We should end up with negative 6/5, right? Because that's what we did the other way. And now we get 5 on the bottom. On the top, it looks like we get 12 minus 28 plus 10 would be 28, negative 28 minus, so we get negative 6. So either way actually works. However, there are certain situations where L'Hopital's rule is the only thing that works. And I want you to use L'Hopital's rule for this, so you're practicing. So all we did is just take the derivative of the top, take the derivative of the bottom separately, and then just try to plug it in. And this time we got a real answer. We did not get an indeterminate form. That's good. All right, let's try a couple more here. So next one is a sine function. All right, now on all of these, you do need to first plug in what there is and show that you get an indeterminate form. So we're going to get the sine of negative 4 pi over negative 4 squared, which is 16. Now sine of 4 pi, negative 4 pi, that is going to be 0. Because at every interval of pi, sine is 0. Because 0, sine 0, pi, 2 pi, 4 pi, 6 pi. Same with negative 1 pi, negative 2 pi, negative 3 pi, negative 4 pi. All zeros. So we get 0 over 0 again. This is indeterminate, which means we're going to use L'Hopital's rule. So I'm just going to do this little L apostrophe H and limit as W goes to negative 4. The derivative of sine is cosine. And we do need to use the chain rule because we got some stuff inside of there. It's pi W instead of just W. So cosine of pi W. And then we take the derivative of the inside. Well, derivative of pi W is just pi. Over the bottom, take the derivative of that. The 16 goes away, leaves just 2W. So now when we plug in, we get the cosine of pi times negative 4 times pi over 2 times negative 4. So we end up with pi times the cosine of negative 4 pi. If you don't know what that is, you can always plug it in your calculator. At cosine, the intervals of pi, if you just think about what cosine looks like, starts up here. And it goes like this. So this is 0. This is pi. This is 2 pi. And then just repeats. So down here, this would be at pi, negative pi, sorry. We're at negative 1. These are negative 1s, and these are positive 1s. So for cosine, all of the even multiples of pi, it's 1. And all the odd ones, like at 1 pi, at 3 pi, 5 pi, it's all negative 1. So in this case, we're at negative 4 pi. That is an even multiple of pi, so it's going to be positive 1. So positive 1 is the cosine of negative 4 pi times pi over negative 8. So it's just negative pi over 8, negative 1/8 pi. Your answer. You would not have been able to get that by doing some factoring. You could factor the bottom, but there's nothing to cancel out with a sign up there. So this would be the only way, other than like making a table or like looking maybe at the graph or something. But you need to be able to do these algebraically, and the way we do that is by using L'Hopital's rule. Okay, next one. All right, so this one's an infinity one. Let's go ahead and just plug it in. So natural log of 3 times infinity. This gets a little abstract when you're talking about infinity. So you might not know off the top of your head what the natural log of 3 times infinity is. I would say maybe draw a picture of what the graph of natural log looks like. If you don't remember, you look it up. Natural log looks like this. It crosses there at 1 and then just continues to like slowly go up to infinity and never crosses 0. So the natural log of 3 times infinity would be infinity because it's going to just keep going. So as you go bigger to infinity, it is infinity. And infinity over infinity squared, well, that's the same thing as infinity over infinity because infinity squared is the same thing as infinity. They're both just concepts. They're not real numbers. So that is an indeterminate form, infinity over infinity. So we need to take L'Hopital's rule. So then we're going to have the limit as t goes to infinity. The natural log of 3t. Remember, for this one, it's 1 over like the u times u prime, essentially. So it's like 1 over 3t times the derivative of 3t, which is 3, over 2t. So let's see what happens here. So now we get, this is just going to actually, this 3's cancel. So we get 1 over t over 2t. All right, so in this one, let's see what we get. This does get a little bit complicated when you start getting these fractions inside of fractions and such. But let's go ahead and plug in infinity and see what happens. So we got 1 over infinity on the top, right? And then we got 2 times infinity on the bottom. So this 1 over infinity, I want you to think back when we first started limits. When you have 1 over infinity, think about what that is. This, if the top is staying the same and the bottom goes to infinity, goes to 0. 1 over any constant over infinity is 0. Because the bottom gets infinitely big, think of like 1 over 1,000 and 1 over 10,000, 1 over 1,000,000, right? It's all trending towards 0. So 1 over infinity is 0. 2 times infinity is infinity. So think about this. 0 over an infinitely big number. Well, 0 over anything is actually 0. 0 over any constant would be a 0. So this actually is 0. It is not an indeterminate form. That's why when we talked about the indeterminate forms.
High school teachers.
All right, sorry guys, the interruption here.
We hope that you have a wonderful winter break. You are free to leave
Pardon
at
the
any
announcement.
time. Please enjoy your time off.
Gotta finish up this video before I head home for Christmas break. So.
And as Mr. Gentile would say, we'll see you next year.
All right, let's proceed. All right, so like I said, that is 0. Because 0 over anything is 0. When we look at the indeterminate forms, notice we said 0 over 0 or an infinite quantity over an infinite quantity. So that is why our answer is 0 instead of an indeterminate number. This is a really key property here. Any constant over infinity is 0. Same with would be plus or minus infinity. That is a very important concept. We learned earlier, but just a refresher there. All right, a few more here. So the next one's a little more complicated. So plug it in, we get the sine of 0, 2 times 0, plus 7 times 0 squared would be 0, minus 2 times 0 would be 0, over 0 times 1 squared, it looks like. Yep, but it doesn't matter. The sine of 0 is 0. 0 plus 0 plus what? Whatever. 0 times 1 squared is 0. So this is indeterminate. All right. So let's take the derivative of both. So L'Hopital's rule. Limit as z goes to 0. The derivative of sine is cosine. So the cosine of 2z times the derivative of 2z, which is 2, plus 7z squared, that would be 14z minus 2, over. Now, bottom's a little complicated because this is a product rule here. Take the derivative of that. So we do 2z times the original second one, plus z squared. Bring the 2 down in front, so times 2, times z plus 1 to the first power, times the derivative of the inside, which is 1. All right, lots going on. Let's try simplifying it here. On the top, we get 2 cosine of 2z plus 14z minus 2 over 2z times z plus 1 squared plus 2z squared z plus 1. All right. On this one, it looks like we're going to get 0 over 0 again. Because we plug in 0 in the top, we get 2 times the cosine of 0, which is 1. So it's 2 times 1 plus 0 minus 2. Well, that ends up being 0. And on the bottom, we got a 0 here and a 0 here, which are going to be multiplied. So that'll stay the same. All right, so this one's kind of nasty. Let's see if we can do it one more time and maybe get it to work. Let's try L'Hopital's rule again. So on the top, we're going to have 2 derivative of cosine is minus sine. So minus 2 sine of 2z times 2 plus 14. I think that will end up being good for us. Over, now the first one we got to do a, looks like we have to do a product rule here. So the derivative of that is going to be 2 times the original second function, z plus 1 squared, plus the original first one, 2z, times the derivative of the second function there, which would be 2 times z plus 1 to the first power times 1. Now I got to do the second one. It's another product rule. Plus 4z times z plus 1 plus the original first one, which is 2z squared, times the derivative of the second one, which is just 1. I know this seems kind of crazy, but I think it's going to work this time. So let's see. Now if we plug in 0, I forgot to put limit as z goes to 0. Negative 2 times the sine of 0 times 2 plus 14. That 14 is going to be good for us. Down here, we've got 2 times 0 plus 1 squared. That's going to be our key one there. Because the rest of these are going to turn to 0 because this one has a z in it, which means we're going to multiply all this stuff by 0. This one has a z in it where we're multiplying by, so that's going to be 0. That's going to be 0. It's going to be 0 plus 0 plus 0. But this one is a good one because it's going to just become 2 times 1 squared. And on the top, the sine of 0 is 0, so this all goes to 0. So we got 14 on top. And then this one down here, thankfully saved us. 2 times 1 squared, which is 2. So 14 over 2, which is 7. Woohoo! So you can see it can be kind of intense. Just do your best on that. But this actually could be something I suppose you could see on the AP test. All right, let's try 2 more, I think. Yep. Okay, the next one, we've got negative infinity squared. Try plugging it in first, and e to the 1 minus negative infinity. So let's talk about what happens there. Negative infinity squared is positive infinity. E to the 1 minus negative, that would become e to the 1 plus infinity. So we definitely got infinity on the top. Think about e. E looks like this as the exponential function. So e to the infinity power or whatever, well, that's just infinitely big number, so that's going to be infinity. So I got infinity over infinity, which means we need to use L'Hopital's rule. Okay, so then we got limit as x goes to negative infinity. Derivative of x squared is 2x. The derivative of e to some function is e to the u times u prime, meaning e, just the original one, and then times the derivative of the exponent. So we got e to the 1 minus x times negative 1, because the derivative of 1 is nothing, and the derivative of negative x is negative 1. So now we've got 2x over negative e to the 1 minus x. We can try this, but we're going to get the same thing again because we're going to get negative infinity on this time. If we try to plug it in, negative infinity over negative e to the infinity. So that would just actually be negative infinity over negative infinity. So we can't do it yet. We got to do it again. This time it should work out okay. Limit as x goes to negative infinity. When we take the derivative of this one here, the derivative of 2x is 2. That's going to be our key there because we got a constant on top. And the derivative of negative e to the 1 minus x will be negative e to the 1 minus x times -1. So that gives us 2 over negative here and here cancel. So 2 over e to the 1 minus x. And the limit as x goes to -infinity. So when we plug that in, the 2 on the top stays. And e to the 1 minus -infinity becomes 1 plus infinity, which would be 2 over infinity. And as we said in the one of the first questions there, any constant over infinity is 0. So that is what we're looking for.